Thank you all for the invitation, I guess, to lead off. I will say I'm very much looking forward to spending an entire week here thinking about these issues and challenges with people, many of whom are part of the census team. And I do have a very big acknowledgement slide, but it's at the end rather than the beginning. And also others that I know have thought hard about these problems. I'm not going to go to my first slide. I'm going to say a few introductory remarks. The Census Bureau acknowledged in 2016 that database reconstruction was a vulnerability of the methods used by the Census Bureau. I'm not going to point fingers at any other statistical agency. By the methods used by the Census Bureau historically for publishing products from censuses, surveys, and other sources. That is, in my view, step one. It's a necessary condition to move from the ad hoc world of disclosure limitation that, now I will point fingers, all statistical agencies have lived in for quite some time, basically since the first mathematical theorems that appeared in statistics, Ivan Falagi's 1972 paper on subtraction attacks. We've lived in that world a long time. We were comfortable in that world because we thought we understood the nature of the problem. And to be frank, in the 1970s and 1980s, we did pretty well understand the nature of that problem. We were going to publish large bound volumes of tabular summaries of data where the principal source for those data was the statistical agency, and the competitive sources outside the statistical agency were at best rare and most often non-existent. In addition, we were going to give the scientific community direct access to the microdata records processed through disclosure limitation so that more general hypotheses than could be embodied in published tables might be studied. And the Census Bureau has been releasing microdata products since 1960. I think you had the world's champion of microdata products here last week, Steve Ruggles, who probably had a slightly different view on the situation than you're going to get from me. It was really important to acknowledge that the world has changed, that the concept of a small group of statisticians locked in the back room doing statistical disclosure limitation using methods that they were sworn to keep secret against attackers that were explicitly naive along dimensions that we're happy to discuss now, that world has changed, and it's changed forever. We can no longer justify using any kinds of models that make arbitrary attacker assumptions. And that is at the heart of the sea change in the way statistical agencies, and not just statistical agencies, it's at the heart of the sea change in which any curator of confidential data thinks about what is exposed to the public from those confidential data. That insight came directly from computer science, and in particular from the cryptographic approach to safe data publication. That insight that you can't make assumptions about the attacker, that you have to give the attacker enormous computational resources, so we'll just say unlimited, and arbitrary outside information if you want to be able to write down a mathematical guarantee of what you can and cannot protect against. That insight is fundamental to the way that the Census Bureau is trying to transform its publication systems. But it has not been universally adopted. And I'm going to talk today about some of the things that you need to think about inside a large institution trying to make a major modification in the way it approaches the publication of its products. So, running a census, it's where the Census Bureau gets its name. You all know that it's in Article 1, Section 2, maybe you don't all know. It's in Article 1, Section 2 of the U.S. Constitution. And while I don't have that clause here for you to examine, most people who see it don't get past the every 10 years, but the last phrase of that clause is, as they shall by law direct. Article 1 is the constitutional construction of the House of Representatives and the Senate, Congress. They is the Congress. So the census is meant to be conducted under the statutory supervision of the Congress, and it is designed to collect the data that underpin our democracy at the very highest level, reapportioning the House of Representatives, at the next level, by statute, providing data to each state to redraw every single legislative district in the country. But that same statute contains a provision that is actually, it's a 1950s era provision, so it's an actually very, very strong statement about what constitutes a privacy breach. A privacy breach, according to that statute, is publishing anything in which the identity of the supplier of that data item can be inferred. Now, there's no mathematical language around that, and it has always been interpreted inside the Census Bureau probabilistically, meaning that you make some risk assessments and then you make some choices and you balance the interests of publication against the interests of privacy loss. But until formal methods for doing this came along, I know I'm being filmed, but I'm going to go ahead and say it, there was a lot of hand-waving going on, and that hand-waving is no longer useful. So basically, what does it mean to acknowledge the database reconstruction vulnerability? I'm not sure that quite a few cryptographers in the audience would necessarily agree with my prioritization here, but this is how I represent it when I have to talk to more general audiences. The first lesson is straight from the database reconstruction theorem. You can't publish too many statistics too accurately. You've got a finite information budget. And a finite information budget gets exhausted with a finite number of publications. We'll see later how many are still on the table for the 2020 census. It challenges the word finite in that statement. Secondly, and this comes straight from the original differential privacy publication, noise infusion is a necessary condition to guard against an informed attacker. So if we're going to get rid of the assumptions about attackers, then we have to accept that noise infusion is necessary. It's not a luxury. It's not something that you can necessarily even specify to behave in the way that you would like it to behave. The randomness that comes from noise infusion is a necessary condition for developing publication systems that protect against arbitrary outside information. That really, really is hard. Finally, the last one might not seem so strange, especially if you came from the cryptographic background, but Kirchhoff's principle applied to data publication basically says that we no longer have to keep any of this secret. There's no advantage to keeping it secret, and there's a positive benefit from the transparency that being public about the algorithms and the parameter values and the code bases. You're going to see a bunch of talks, that's a technical term, today and through the rest of the week by people working in collaboration with the Census Bureau, or in some cases actually employees of the Census Bureau. We have a special category of employees for academic collaborators. And all of that mathematics is going into the public domain, and the code base is going into the public domain. The code bases that we used for the 18 end-to-end test, which I'll show you some pictures of in a few minutes, that code base is going into the public domain on March 28th. We might miss that deadline, but we are working hard not to. And if we miss it, we won't miss it by more than a few days. All right? Transparency really is a benefit. All right. It took a while for us to complete the internal experiments necessary to put the nail in the coffin of traditional methods for publishing decennial censuses, universe enumerations. I think there are actually some people in the room who were among the ones I consulted in late 2016 to say, I think this is feasible, but the set of people who understand census data and the set of people who understand database reconstruction attacks doesn't have any intersection. So can we create enough intersection so that I can get a team at the Census Bureau to do a real database reconstruction attack? The only reason that I am not reporting detailed scientific information from that is that I've had these two slides cleared, not just by the Census Bureau, but by some of the target journals that we are going to submit to. I'm an economist. I'm used to operating in the open working paper regime, but that's not the regime that we're operating in here. So they will be public, but they will be already through external peer review before they're made public. What I'm talking about today isn't going to change very much. So we did a record level reconstruction of the person data in the 2010 census. That means that we constructed a record for all 308,745,538 people when testifying in the 3 trials that I had to testify in, finishing up on January 31st in Maryland. That number was used so many times that I now say it just as trippingly as my colleagues who were around when that number was finalized. So one record for every single one. 5 publication variables. The block that the person lived in. If you're familiar with census geography, there were 11 million blocks in the 2010 census. 6.2 million of them actually had people in them, and we didn't protect whether a block was occupied or not, so that's a public number. All right. Your sex, your age in years, your race, all 63 categories that the OMB classification permits. The only one that's not permitted is none of the above. If you actually left it blank, you got imputed. So there's and ethnicity, Hispanic or not. So just 5 variables, but one for every single person in the US. We took the reconstructed microdata and used fairly straightforward exact record linkage techniques against 4 commercial databases that were acquired between 2009 and 2011 in support of the 2010 census to recover name and address, PII, as it's known in the trade. For every record that we were able to recover PII, we called that a putative re-identification. That basically means if you're an external attacker, you would think that this is the census data associated with this person's name and address. We then took the complete record, not just the part we used for the re-identification attack, the complete record, name, address, block, sex, age, race, and ethnicity, and compared it to the truth. Right. So that's a confirmed re-identification when that happens. And the harm in that experiment is the self-response on race and ethnicity isn't available in any other database, neither commercial nor governmental. That's entirely internal to the Census Bureau. So you would learn the self-response on race and ethnicity exactly rather than statistically. All right, what did we find? Well, the first thing is because of the way the publication tables were constructed, there's never any error in the block ID. There's exactly the right number of records in every single one of those 6.2 million blocks, and there's never any error in whether that record is associated with a person who is not of voting age or a person who was age 18 years or older. So those are reconstructed exactly. The block, sex, age, race, and ethnicity in the reconstructed data exactly match 46% of the population in the confidential data on those 5 variables. So that says that the image of the confidential data that you can build outside the firewall has 46% of the records exactly right on those 5 variables. If you allow age to vary by plus or minus 1 year, then it has 71%, or 219 million of the 309 million records correct. Why is that salient? That's salient because in the confidential data on those same 5 variables, more than 50% of the records are unique in the population. There's only one record that looks like that in the whole population. That is the traditional way of signaling disclosure risk, and the exact percentage is confidential. That's why I've just given you the approved, not even one significant digit, but more than a half. So you already know that if the system was supposed to be designed to protect against this kind of risk, that it has a vulnerability because you got 46% of them exactly right, and in the confidential data, in that set of variables, more than half the records are population uniques. When we did the putative re-identification, 45% of those records, just using block, sex, and age, acquired a unique name and address. So that's a 45% putative re-identification rate. I think in some literatures that's called the recall rate. The recall rate isn't 100%. The recall rate is 45%, but that's probably an underestimate because the denominator is certainly not 309,745,538. Neither the Census Bureau nor any of the commercial databases now or ever has full information on the entire population of the United States, even using consistent rules for what that might be. Right. When we went to confirm those putative re-identifications, 38% of them confirmed. So that's 52 million people, or 17% of the population. That confirmation rate is multiple orders of magnitude bigger than the largest confirmation rate that the Census Bureau has ever published for this kind of study, which was based on a study using the American Community Survey that was published in 2013, where the confirmation rate was, it's in the speaker notes, I think, but I can't see my speaker notes, something like 0.017%. And the recall rate was 300 odd cases out of 2.2 million. So you can take my word for it. There's not a single person in the Census Bureau who thought that either the putative re-identification rate or the confirmation rate would ever be this high on a relatively straightforward experiment like this. So this just confirms, we have already acknowledged that, oh, I forgot to read it. I'm speaking for myself and not for the Census Bureau. The Census Bureau had already acknowledged that this was a vulnerability. This just confirmed it. And in my view, it's basically a waste of time to keep beating up on these kinds of experiments to see how bad it might be in addition to how bad it already is. Or, as the reporter for the Financial Times said, a result so shocking that the Commerce Department was brave to release it. I don't know that it was all that shocking, but it was definitely, as far as I'm concerned, the nail in the coffin. There's nothing left to talk about here. It's a real vulnerability. It really happened, and it has to be fixed. So that brings me to what I consider to be the hardest lesson in modern data science, which is the combined implication of the database reconstruction theorem and the formerly private method of analyzing systems that are designed to address it. Getting your arms around the information constraint on publication is really, 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 really hard. And challenging inside an organization where you have to address it essentially at every turn. There are branches all over the Census Bureau that are used to having direct access to the confidential data. We had to find them, we had to identify their methods, and we had to bring them under the privacy loss budget. It really was the death knell for traditional methods of publication, and I'm not just talking about statistical agencies. It's the figure that I'm sure you knew I was going to put up. I deliberately don't label the privacy loss axis in this figure because everybody in this room knows that this is algorithmically dependent. The goal of the computer scientists and the engineers of these systems is to push this curve describing the relationship between privacy loss, epsilon, and accuracy as close to the 0-100% point as you can, like getting an efficient predictor model and treating this like a receiver operating characteristics curve. All right? But the two extremes, no accuracy and no privacy, are what the 0-1 nature of decision making in the past has focused on, and we need to learn how to focus on this frontier. To make it easier to focus on this frontier, I deliberately set it up so that This is not accuracy from all sources of error in the data product. This is the incremental loss of accuracy associated with the disclosure limitation system, the privacy protection system. So that's why it's natural that as you increase the privacy loss budget, it's going to asymptote to 100% accuracy. You should engineer that into the systems. If they don't have the property that when you give the system no constraints, it delivers back the same answer you would have gotten if you had skipped the system altogether, there's something wrong with the engineering of the algorithms. But in many cases, that 100% accuracy is just as accurate as the underlying data can answer the question. It's not perfectly accurate answer to the question. So in the case of a census, it ignores the errors associated with coverage. Did we get complete coverage in your geographic area? Generally speaking, those are measured in terms of net undercounts and differential net undercounts. It ignores the errors associated with the processing of the someplace between 25 and 35% of the records that didn't come from a direct self-response by the household. They came from either non-response follow-up or they were incomplete and were finished with other forms of what we call item allocation. Most people just call missing data imputation. None of that error is reflected in that 100% accuracy. So, one slide of economics. It's inefficient to be inside the frontier. You don't want to use algorithms that deliberately waste either the privacy loss budget or accuracy. And it's infeasible to be above the frontier. And I might add, we don't actually know where that frontier is. It's very dependent on the set of things that you want to publish and how you decide that the accuracy needs to be assessed. I lied, there's 2 economics slides. But no matter how you do it, whether you're there or there, and I've eliminated all of the judgmental labels on this, whether you're there or there, that's a social choice. And the tools that we use to make that social choice don't come from computer science. Maybe you don't think they come from economics either, but I need to understand the willingness to pay for increased accuracy from foregone privacy. And that is fundamentally a question about the preferences of the population that you're running the statistics on, or in the case of the census, the preferences of the curators, that would be the Census Bureau, over which things to give accuracy and which things to give less accuracy to, and that's essentially embodied in those decisions. So we can talk about that, but that's probably not the strong suit. I'll take questions about it. But we are trying to collect more data on actual population preferences and on the preferences of the subpopulations that use certain parts of the census publications. In particular, data on how accurate data that are used to draw redistricting have to be. All right. So to address the database reconstruction vulnerability for the 2020 census, the Census Bureau implemented differential privacy. Effectively, at least as far as I can tell, because it was the last thing standing when you got to the decision, well, you've got a vulnerability and you have to address it. What are your available choices? Formal privacy models, and from the formal privacy models in 2016, and Dan remembers sitting in my office and us going over whether we could actually use generalizations or whether we should just stick to the fundamental definition. We decided at that time to stick to the fundamental definition because that was the most usable stuff out there for that. So we're trying to demonstrate by actually applying this to our flagship product. Again, I'm not speaking for the Census Bureau, but I am using the first person plural. I'm not quite sure why. The intention is to demonstrate that you can release statistical data that are fit for their intended uses, and that you can bring an entire publication system into a formal privacy loss budget. It was a heavy lift when we set out in 2016. It remains a heavy lift, and here's why. There's only 2 things that the Constitution and the statutes require the Census Bureau to publish from the census: the reapportionment of the House of Representatives and the file known as PL94-171 redistricting data, the data that we give each state for drawing legislative districts, whose form is negotiated over the whole decade. And those negotiations were largely complete in 2016 when the new chief scientist walked in and suggested that they might want to consider doing some things a little bit differently. Just in the disclosure avoidance procedure, not the form of the tables has stayed fixed. What I promised my colleagues at the Census Bureau was that we would be able to do those things on time and that the data product would be of the quality that they expect. I'll show you the names of the team. The team has delivered that. That's remarkable progress in and of itself, but it doesn't come close to the rest of what the general user community expects from a census of population. And you'll hear some talk about Summary File 1 later today. Even Summary File 1 turns out to be the tip of the iceberg. When asked to gather all of the proposed uses of the 2020 census and then pass them through formal analysis of how many queries that involved on the underlying database, the number in red on this slide is to 2 significant digits the answer that comes back. All right, 100 billion. Even I had come nowhere near doing it informally by looking at the different table summaries. Partly because I hadn't looked past Summary File 2 to the summary files for American Indians and Alaska Natives, which are 3 times as disclosive as the 30 billion queries in Summary File 2. That's just mathematically impossible to do that with the level of accuracy that has previously been used with a finite privacy loss budget. I think the team put it at someplace between 45 and 100, an epsilon that might address a substantial subset of these with accuracy similar to the way they had been published in 2010. So that's a huge challenge. So here's my kudos to the team. They've done a lot of work. I'm going to show you some of it in a second. We've got methods for quantifying and displaying system-wide trade-offs between accuracy and privacy loss, and between the allocation of accuracy to one set of tables and, versus another set of tables. It started in 2016, so we are slightly more than 2 years into it. In my view, that was a monumental achievement, but it doesn't come close to meeting the concerns of the user community. But we'll have some time to talk about that. But let me just show you what you can do. All right. Dan Kiefer, in his talk, I think he's the next one, is going to take you through the technical issues here. One of them is that some people think that some numbers have to be published without disclosure avoidance error. I will just say that there is no legal justification for that statement because Utah v. Evans, the 2002 case, the last time somebody from the Census Bureau appeared in testimony that got to the Supreme Court, that case determined that the Census Bureau is allowed to use accepted statistical methods in preparing its publications. It was about count imputation. If you don't know what count imputation is, at the very end of the process of counting for every address in the United States during the census, there's some addresses left over. They haven't been accounted for. We don't know if they're fake, fake's not the right word. They don't know if they should have been deleted from our address list, or if they're vacant, or if they're occupied. So they go through a statistical model. And at 1.16 million people in 2010 were put into the census, and not all in the same state or in equal proportions across the states, by that process. So not even the numbers that go into reapportionment have to be published, quote, exactly as enumerated. However, that is the kind of policy discussion that takes a long time to have. So this chart shows you what happens when you set the state population as an invariant, meaning there's no differential privacy noise in a single number. These experiments were done on the state of Rhode Island using its 2010 data. So in each case, the only invariant in these figures is the state population. I forget what it is in Rhode Island, but it doesn't matter. You can look it up. It was a public number. All right. And it had no disclosure avoidance noise in it in 2010 either. All right. The accuracy measure is take all the tables in the redistricting data at the particular level of geography here, state, county, tract, or block. Take all of them, calculate the total variation distance between that table and the truth, average it over all the tables in the workload, and subtract that number from 1. So this may not help you guys, but it helps many statistical audiences. The total variation, average total variation distance is like the percentage of entries in the table that would have to be flipped in order to get back to the true table. So when the accuracy is 100%, it means that the protected table is essentially identical to the true table. And I'll show you in a second one of these things organized with privacy loss on the x-axis and accuracy on the y-axis. But this set of slides is designed to show you on the x-axis, over at 0, all of the privacy loss budget is assigned to the redistricting data. And over at 1, all of the privacy loss budget is assigned to the flagship counterpart in summary file 1, which is the age by sex tables. So the redistricting data are detailed data on race and ethnicity, and the only age variable they have them are whether you're voting age or not. And the sex by age tables are detailed data on the population pyramid in each of those geographies, sex by age. So the first thing you can see is those tables are highly correlated, and as a consequence, at the state level, it makes almost no difference. I don't even need to tell you what the values of epsilon are on each of those curves or what the table sets reflected. By the time you get up to a state the size of Rhode Island, there's essentially no loss of accuracy, except, is there a pointer on this? Yes. Except out here. This slide doesn't project very well, does it? Out here. My slides are public, and I will be happy to send them to anyone, and you're free to redistribute them. You can also see that it really doesn't matter for the 5 counties in Rhode Island. Essentially, where you set that privacy loss budget, whether you put it all in the redistricting data or you put it all on the summary file data, doesn't matter. It starts to matter at the level of a tract. A tract has approximately 4,000 people in it. All right. So these tracts, it matters. Let me see if I can remember all the scales here. Again, I'm having trouble reading my speaker notes. Yeah. All right. So the red lines are the summary file 1, the age and sex pyramids, okay? And the black lines are the redistricting data. So all of the values of epsilon are stacked on top of each other here, so it doesn't really matter which is which, even at the tract level. There's a lot more cells in this sex by age table than in the redistricting ones. So if you don't give them any of the privacy loss budget, all of this accuracy is due to those correlations with the redistricting data. But even if you give them all the accuracy, at the tract level, for some values of epsilon, each of these curves is for a separate value of epsilon, starting at 0.25, I believe. Yes, so that's 0.25. And the highest one is 10. 10 is coincident with this. This is 3. So the key thing here is all of these redistricting ones are pinned up against accuracy of 1. Most voting districts are quite a bit bigger than a tract. So this says that the allocation of the privacy loss in the top-down algorithm that Dan's going to explain to you essentially delivers data that are as accurate as you could hope for, as long as the population inside the voting district is bigger than a tract. Now that statement is qualified, and he'll spend a lot more time on this, by the fact that voting districts aren't coincident with tract borders. However, these county and state boundaries and many of these tract boundaries are coincident with the boundaries of voting districts because of the way they're constructed. And so if you build the accuracy hierarchy in on a fixed geographic hierarchy like block, tract, county, and state, that also constrains the arbitrary voting districts, they're going to inherit some of the accuracy. And I didn't bring any of these tables with me because they haven't been graphed up and released, but that statement is true. All right. So finally you get to the block level. All right. And you can see that for the age pyramids, it's hard to get accuracy that gets anywhere near 1. For the redistricting data, you have to use very large privacy loss budgets to get accuracy anywhere near 1. And the one you can't see, the gray one, is the population table, which is here. It's the ones coming off here. There's also noise in the population levels. So you need to, and that's correlated with both the PL94 and SF1 tables. All right. So what do we do? Now I've taken the same assumptions and plotted this out with the privacy loss on the horizontal axis and the accuracy on the vertical axis. This is the block level accuracy. To get the block level accuracy anywhere near 100%, you have to give that whole operation a fairly large privacy loss budget. But if you look, it starts to bend in here. And in fact, we set the privacy loss budget there, not quite where it is on the ray coming out of the origin. We set it there, 0.25, because as soon as you get to the tract level, it's 0.98. As soon as you get to the county and state level, it's essentially 100%. If the use case is for populations, geographic areas that have populations that resemble a tract, this is more accurate than the data that was used in 2010 on some criteria, less accurate on others, but certainly comparable. You don't need accurate block level data to build arbitrary districts. You need accurate data that aggregate properly as you build up these arbitrary shapes, and those arbitrary shapes need to be plausibly constrained by, well, they're obviously constrained by block. That's the pixel. You can't use anything but a block. Many of the boundaries are constrained by tract. Almost all political boundaries are constrained by counties and states. So the use case fits, and there's no reason to go out here to 3 to get the block data accurate, and there's very good reasons not to. And I spent most of the last year on 7 days in testimony discussing the very good reason not to go out here for the block level data. One of the variables in 2020 is likely to be citizenship.
John?
Yep.
So that's for redistricting. What are the top 2 or 3 cases for which somebody would argue for block level statistics? Use cases.
You don't want me to do my rest of my slides? Yeah, I said I'd take questions. So the use case for the sex by age pyramids is state, county, and city demographers building population models, predicting the number of school-age children and other the sizes of the retired communities and other things that are strongly correlated with public services. And in our collection of use cases, those are almost always done at political boundaries. The least dense political boundary that the Census Bureau routinely publishes data for is called a place or minor civil division. In some states, the minor civil division substitutes for counties, but in most states, the minor civil divisions are subsets of counties. They generally respect the county or county equivalent borders, but they don't respect tract borders. So if you look at a standard census geographic hierarchy, they're built on blocks, they bypass the tract, and they go straight to the county in that hierarchy. Okay? There's about 15,000 of them, which is still not a huge number of places, but the Population Estimates Program has agreed to design differentially private publications for minor civil divisions and places in exchange for being granted direct access to the 2020 census in the years between 2020 and 2030. So they still haven't been given their privacy loss budget, but that they're working on. That's the best use case that I know. So as Jerome's question alluded to, this is just the tip of the iceberg. Probably the most used product from a census that is not statutorily dictated is what we have called the demographic profiles. They are summaries that have traditionally been built by taking all the tables in Summary File 1 and aggregating them to that minor civil division place level and then doing statistical summaries of them. We can handle almost all of the workload from the demographic profiles for persons and for households. I'll get to the query that we can't do in a second. And answer them with a reasonable privacy loss budget. So that's nice. But exactly what privacy loss budget should we use for the ensemble of the products? Right. Should we go out to epsilon of 8.9? I can pick on that number because that's the epsilon on the map that multiple people in the room participated in engineering in 2008. So that's a big epsilon that the Census Bureau used starting in 2008 and is still the epsilon in that product. How do you go about inside an agency saying, okay, build the use case for your users, and then if you go outside the agency, I think we may have heard some good examples of this last week. The answer to the question is how you should allocate the privacy loss budget is you should make my project perfect and let the rest of the people deal with the noise. And I wish I were making that answer up. So that's not feasible. The statute is silent on granting any other curators the authority to manage the privacy loss budget, so it's going to have to be done by the senior executives at the Census Bureau. It's done in the Data Stewardship Executive Policy Committee, which consists entirely of career civil servants and is chaired by the Deputy Director and Chief Operating Officer, currently Ron Jarman. So that's the answer to how we're going to deal with the privacy loss policy. Managing the invariance is a really hard problem. We'll probably have more discussion of that after Dan shows you just how hard it was to engineer the ability to have invariance into the system. But in addition, the researchers on the census team did the original mathematics for what it means to have invariance in one of these publication systems. They were outside the scope of the differential privacy literature. So the mathematical definition is that your publication system has two algorithms operating on it. One of them gives exact answers and the other one gives differentially private answers, constrained to have the exact answers be true. So once you set that problem up, you want to know how much to blame on the invariance and how much to blame on the privacy preserving publication system. That was a hard question to answer, and it has a very unsatisfying answer if you're trying to manage policy. The presence of invariance implies, because it's a violation of the fundamental theorem of information recovery, implies that there are some situations for which there's infinite privacy loss. Okay? And it's relatively easy if you're trained in the cryptographic tradition to find those cases so you can see what it is. But invariants come from either real policy or interpretation of policy, and they're not going to go away just because most of the people in this room say your systems shouldn't have invariance. They inherently leak an infinite amount of information under certain circumstances, and you're trying to design the systems to contain those circumstances, to not make assumptions about the attacker's information set. So there isn't an obvious way to quantify what happens when you put invariance in a system. But there are some mathematical approaches that I think would be useful. They are built on the following intuition. Bounded differential privacy admits one invariant. The number of records in the database is public. And it's pretty well understood what that does to the semantics of the differentially private remaining publications. Having 50 state population invariants, technically 51, but Washington, D.C. doesn't actually go into the redistricting, the reapportionment algorithm. Having 51 state population invariants, there must be some sense in which there are more states of the world that allows information leakage for than when there's only one. Similarly, having 11 million block level population invariants, there must be more states of the world in which that allows infinite information leakage than with 50. So some of the team are trying to make those statements precise because I don't want to go to the Data Stewardship Executive Policy Committee and say, we have to consider how to do reapportionment in the presence of differential privacy and not have real mathematics underlying that decision. We basically owe it to successor policymaking groups at the Census Bureau to not use these kinds of arguments anymore. But that's a really hard argument. I don't know how to do externally reviewable quantification, but not in the sense of the differential privacy quantification, of what it means to either have a statutorily imposed invariant or to act as if you had one. And I will remind you that there is no statute that says, or judicial interpretation that says, that the state populations should be exempted from the confidentiality protection system. Next hard question. The self-responses and internally edited versions of the census, I said that very carefully because it excludes anything that came in from administrative records, become public 72 years after the census. And so you would like the privacy loss budget to decay naturally over that 72-year period. I think that might actually be one that can be reasonably thought about. One of the prime claimants to the privacy loss budget over the first decade is the Population Estimates Program, which reuses the data from the census so that it can combine it with data from other sources to get estimates of the change in the population in each of those 15,000 minor civil divisions and places. How do we manage the access of external researchers to the census? There is the perception that you just go into the RDC and you get granted access to historical censuses. That's actually not true. When you go into the RDC, you get granted access to a particular variant of the historical censuses that, at least in principle, was designed to have privacy protections in it. So the principle that what you use in the restricted access environment has privacy protections in it is already built in. Nevertheless, I think it's now incumbent on researchers who want to use the confidential versions of the 2020 census to include in their proposal the differentially private analysis system that they propose to use. That's going to have to get peer reviewed because it's really, really easy not to get that right. Spoken from someone who has been down that rabbit hole many times. It's also really easy not to program it right. So we need to figure out how to ensure that it was properly implemented. And finally, that means we're going to have to queue those up, and the Data Stewardship Executive Policy Committee is going to have to decide how much, if any, epsilon each one gets and add that to our accumulated privacy loss budget. To say that we haven't set that system up yet would be to basically state the obvious. So, if we set that up for external users, does the same thing apply to internal users? I think the answer to that question has to be yes. So, anyway, my last slide. I wanted to acknowledge, I think that this is a reasonably complete list of the major contributors to the work that has been done inside the Census Bureau. Some of them are computer scientists, statisticians sitting in this room. Others are full-time census employees. Some come from the subject matter areas. Some come from the statistical areas. I don't know whether to think of this as a big team or a large team. It has borne the brunt of the last 2.5 years worth of work, and I have mostly been summarizing the really great work that they did. My slides include some links to some of the things that I have talked about in our implementation. See that I have a date wrong on that last one. I might fix that. That was December 6th of 2020, or 2019. Yeah, that error escaped many proofreaders. All right. So I'll take questions.
To the speaker to leave plenty of time for questions, so we have 15 minutes. One thing I want to add before taking question is that We will have two panels, one tomorrow and one on Thursday. The one of tomorrow will be on how to set in the privacy budget. So it was related to some of the questions we saw during John talks. And the one on Thursday will be on where our statistical agency going. So also related, of course, to the talk by John. Yeah. Question?
Yeah.
So, can you speak some to the benefits of disclosing the techniques for adding noise?
Yes.
And kind of to give you like a softball question, I remember a debacle from a few years ago where it was discovered that the microdata like messed up badly the data for senior citizens, and it's less likely to happen for the methods that you're advocating. So can you kind of tell us what work is done on that side?
Do you want the history of the debacle, which sounds like something that Steve Ruggles told you about last week, or do you want what we're doing about it? Or both?
So you can address the audience.
Okay. So among the ad hoc systems that are used to protect confidentiality in all of our current products are some algorithms that add noise to selected variables inside the microdata before they're passed to tabulation or before they are released as a part of a public use microsample. It was documented that the algorithms that were used for the original 2000 census public use microsample and the public use microsamples from the American Community Survey until the middle of the 2000s, I forget the exact year that the problem was discovered and published in 2010 by researchers working at the Minnesota Population Center. That's Steve Ruggles Institute. What they did was they compared what would now seem like a pretty obvious mistake, but they compared the tabular summaries, which had not been passed through the same disclosure limitation methods, to the things that came out of the microdata, assessing the incremental noise that was added to the microdata. And the age profiles, the sex age profiles for people age 65 and older were all wacky because of a programming error in the disclosure limitation, which would probably not have been exposed if we hadn't done it two ways. There's a lot of more discussion of that in my paper with Ian, which appeared in an economics journal where it would do the users some good, but not the computer scientists, the Brookings papers on economic activity. So what we're doing for the formerly private 2020 census is, first of all, we're making all the algorithms public so that you can see exactly where the noise was infused. We have prepared a special extract from the 1940 census, which is public, that's being curated by the IPMs, again, Ruggles Institute, so that it doesn't get revised when they routinely improve their historical data assets. So this one won't be revised, it's the same inputs. When we release the code base for what we did for the 2018 end-to-end test, there will be a wrapper that loads a comparable extract, it's not on cases but on variables, of that 1940 PUMS so that you can play with it. You can change the privacy loss budget, you can change allocation assumptions in that privacy loss budget. It doesn't do the full set of tables, it only does the redistricting tables, but we're trying to help the user community understand where the noise comes from and what its consequences are. We're also going to release some number of runs from the data that underlie this chart so that you can do redistricting plans on them and see the intrinsic variability. Good enough? Adam.
So, I guess a couple of questions. So one, in addition to providing the code, are you thinking of providing any kind of more easily interpretable evaluation of error, like error bars or things like when publishing the tables?
So, thanks for that question. The answer is that I want to publish something that looks like error bars. And that is an open discussion. What we've committed to is, to the extent that the algorithms require additional calculations in order for those error bars to be computable outside the firewall, we will devote privacy loss budget to that. So there's some data dependence in the algorithms. You'll see when Dan goes through them that there's some data dependence that's unavoidable, and so you can't just take epsilon and simulate it from our software. You need to know a few bias correction terms that we think we know how to calculate. So if we can't do it, I have no doubt that an outside value-added resupplier will do it. My guess is that exactly 2 will do it, and they will have red and blue labels on them, but I did say that with the camera on. I hope that's interpreted in the spirit that it was meant. The point of open access to the code is not to have people pat you on the back. It's basically to have people find your mistakes, and competitive use of the programs is going to do that a whole lot better than me sending them through many rounds of correction inside the Bureau. Yeah, I'll let you follow up.
Follow-up, quick question. So, do you have a sense of how those errors that you plotted in the table that's on the slide there, those total variation distance errors, like how they're distributed across different tracts or blocks? I would imagine in relative terms they tend to concentrate in the smaller.
So virtually everything you want to know, you see in summary statistics that are stratified by the estimated population size in whatever the geographic area is. I didn't bring any of those with me, but we have certainly looked at those, and that's the right way to think about it, I think. This algorithm was tuned so that the accuracy improved as the population in the geographic unit increased, and so that the main things you want to look at the error of are there. These charts here actually show you how the error has been allocated between the sex by age table and the race and ethnicity tables. So there's already some things you can learn, like that the sex by age tables are at the block level are intrinsically harder to get more accurate. It's a bigger workload. Frauke.
John, fascinating and tremendous amount of work. I mean, every time I hear this, I'm like, whoa, just so few people, so much work. But one thing, a very naive question that sort of hadn't occurred to me in the past, but I'm sure you got before. So these 38% in the re-identification attack. I was wondering if not knowing any census data, not having access to them, if I were to take the Axiom data or some other data that I can purchase, as we often do in the survey firms, right, and would try to predict race and ethnicity, given that this is a small number of categories, how good what's the probability of getting it right?
So one of the assessments we're doing of the Reconstruction is what kind of statistics can you compute from the reconstructed microdata that would be predictive of your ability to either putatively re-identify or confirmed re-identify. So we're looking at population uniqueness statistics and the other side of that, homophily statistics, that you can compute once you've reconstructed the data. Constructing the right counterfactual for the information gain is trickier because basically you've already demonstrated that the block level tables were too disclosive. So saying that you don't get much of an information gain over the already too disclosive block level tables is just repeating the charge.
No, I meant without those tables.
But then what's my that's right. So what's the appropriate counterfactual for the information I'd be able to learn in the absence of the block level tables? And I don't know, the American Community Survey tables, they might have the same problem.
I was thinking of, I mean, if we just sort of think in the many different instances where people have to report their race or sex or age.
So on the commercial, so to keep the exercise fair, we used commercial data from 2009 to 2011. There's almost no race and ethnicity data in those. Mm-hmm. So it is and every one of those companies that had that variable in there said it was modeled. which doesn't surprise me. I'm guessing I even know what it was modeled on, but I'm not going to go there. So it is really hard to construct a counterfactual that's a reasonable summary of what you could have learned if we hadn't published these enormously disclosive tables in the first place.
Right. There are a bunch of other questions, but I think we need to keep on time because there are people watching.
That's your job. Yeah.
So maybe I ask to the people that have questions to ask them to John during the coffee break. And let's thank again John and enjoy the coffee break.